Welcome to our journey into the world of machine learning and natural language processing. Before we dive into the complexities of dense embeddings, let's start with the basics. One-hot encoding. Imagine you have a list of words: cat, dog, and bird. To a machine, these words are just strings of characters that don't inherently convey any meaning. To make these words understandable to a machine, we need to convert them into numerical form. This is where one-hot encoding comes into play. One-hot encoding is a simple yet powerful technique where each word is represented as a vector. Vector illustration of word labeled cat. In our example, the word cat can be represented as 100 vector labeled dog, representation dog as 010 vector illustration labeled bird, with vector representation and bird as 001. Most important point to note is that each vector is as long as the number of unique words in our list, and only one element in the vector is hot or set to 1, while the rest are set to 0, hence the name one-hot encoding. But why do we need this? The primary reason is that machines need numerical data to perform computations. One-hot encoding transforms categorical data into a numerical format, making it easier for algorithms to process and learn from the data. However, while one-hot encoding is effective for small vocabularies, it has its limitations. As we encounter larger datasets, the vectors become increasingly sparse, lots of zeros, and computationally expensive. This is where dense embeddings come into the picture, offering a more efficient and meaningful way to represent words. Stay tuned as we explore why dense embeddings beat one-hot vectors in the next chapter. Hey folks! Welcome back to my channel. Today, I'm diving into an essential topic for all you data scientists out there: why dense embeddings are superior to one-hot vectors. So, let's get started by defining what a one-hot vector is. Imagine you have a vocabulary of 5 words: cat, dog, fish, apple, and banana. In a one-hot encoding system, each word is represented by a vector where only one element is 1 and the rest are 0. For example, cat is 10000 while dog is 01000. Now here's the kicker. These vectors are sparse, long, and meaningless. Why? Because dog and cat, which are pets and somewhat similar, are just as unrelated as dog and banana. This lack of meaning is a major limitation, so what's the alternative? Dense embedding vectors. Instead of using long, mostly zero vectors, embedding layers convert each word into a dense vector. These vectors typically have dimensions like 300, 512, 768, or even 2048. For instance, the word cat might be represented as 0.12, 0.33, 0.76, 0.07 in a 300-dimensional embedding. Notice something different? These numbers are real, not binary, and they capture meaning. Cat and dog will have similar vectors, while banana will be quite different. Now let's talk about what 300D or 768D actually means. The D stands for dimensions. A 300D vector is a list of 300 numbers that capture the essence of a word. A 768D vector is longer and can capture richer meanings. This is common in advanced models like BERT or GPT. Think of it like describing something in a multidimensional way. In 2D, you might describe an object by height and weight. In 300D, you describe a word using 300 hidden features, learned automatically during training. So why are dense embeddings better? Let's break it down. One-hot vectors don't carry meaning, but dense embeddings do. Dense embeddings are more efficient. Dense embeddings show similarity, one-hot vectors don't. Dense embeddings are learned during training. To sum it up, dense embeddings are a game changer for capturing the nuanced meanings of words. They make our models more efficient, meaningful, and intelligent. If this has been helpful, make sure to give it a thumbs up and subscribe for more insights. Thanks for watching.